My name is Steve Sorge. I'm PAC International Sales Director, and with me today is our INCE Board Certified Acoustician, Mike Raley. And just a little housekeeping, if you have questions during the presentation, please put those into the question box there. And if I can answer them, I'll answer them during the presentation. Otherwise, we can pick them up at the very end where we'll have a short Q&A. Take it away, Mike.
All right, yeah, thanks, Steve. So yeah, as Steve said, I am an INCE board certified acoustician, and I just kind of want to give a little caveat here. So I'm talking about acoustics and fire in this presentation, and acoustics is my area of expertise. Fire is not. And so really what this presentation is talking about kind of what I've learned over the years, especially in the 3 years I've worked at PAC, about fire, design for fire, fire-rated assemblies, that kind of thing, and how it relates to acoustics. And the things I've learned about where those things are often at conflict with each other, at odds with each other, and discussing sort of how to navigate that. So I'm not necessarily giving very prescriptive design solutions, more things to look out for, and here's some sort of directions to go with those things. So hopefully that makes sense, and hopefully there's some useful information in here for all of you. So just as an overview of kind of what we're going to talk about, just to sort of like lay the groundwork for the rest of the discussion, we'll talk about some acoustics basics, and then we'll talk about fire rating basics. And I tend to spend a lot of time in the multifamily space, and that's kind of what this is geared towards primarily, but a lot of what we'll talk about will apply to other things as well. But like the acoustics basics, I'll talk about code for multifamily and things like that. Next section is devil is in the details. We're going to talk about some of the details of assemblies, acoustics ratings, fire ratings, things like that, and why they matter and how they might sort of catch you up. And then we're going to talk about tensions in the design teams. I've got this cool little animated graphic that we'll go through, talk through some tensions between different folks in the design team. And then rules of thumb are dangerous. We'll just give an example of that, kind of walk through it. And then we're going to go through some examples of kind of, assemblies, designs, intersection details, construction details, things like that, and talk about how fire and acoustics sort of play together, don't play nicely in those different designs. And then last but not least, hopefully at the end, we'll have time for Q&A. Throughout this, if you have any questions, feel free to tap him into the questions thing. Steve will be watching those for me. He'll respond to those in the chat that he can, and if we've got time, he'll bring some up to me and I'll do my best to answer them. So with all that, let's get into it. So like I said, acoustics basics, we'll start here. And so we have code minimums for acoustics, and a lot of times that's sort of the driving factor for our need for noise control in a building, especially multifamily. There are other codes for other types of spaces. There's codes or guidelines for designing schools, right? There's codes or guidelines for hospitals. Government has their own, the GSA, and different government groups have their own. There's acoustics requirements within LEED and WELL and all of these different things, right? And a lot of them use fairly similar terminology and work somewhat similarly to the building code for multifamily. So the ICC code minimums for multifamily construction, if you're using lab test reports, then the ratings minimums are an SEC 50 for airborne sound and an IIC 50 for impact sound. And if you're using a field rating, so you're actually going to go test that building like in situ, you get a field rating, then the requirements are NNIC 45 for airborne sound and NISR 45 for impact sound. Now those metrics, the NNIC and the NISR, those have only been specified since like the latest, I think 2021 code cycle. Prior to that, it actually didn't specify a metric at all. It just said, if it's in the field, it's got to be a 45. But there's a sort of a grab bag of different terms for acoustic field ratings, and it didn't actually specify those. The other thing that I want to add here to this discussion is that these are code minimums. And with acoustical performance especially, the code minimum isn't always enough, right? And you think about sort of the context of people's expectations when they're moving into an apartment or a condo, right? So, student housing, going in as a student university, you don't necessarily expect your student housing to be that quiet. However, if you've got like condos, higher end condos, in a place where you've got a lot of retirees, you've got a lot of people that are sort of empty nesters and they're downsizing and they're moving into multifamily housing for the first time, maybe in many decades or maybe ever in their life. Their expectations for quiet are probably going to be very different and much higher than college students, right? So we got to consider those, and maybe the code minimums aren't going to be enough. So there's this quote that I use a lot, and that's here on the screen. With the current level of performance specified by the building code, a large percentage of people are highly annoyed by noises from their neighbors, leading to a reduced quality of life and possibly to negative health effects. Now I'm an acoustician working for a product manufacturer, so you're like, oh, well, you've got this ulterior motivation. Of course you'll put up a quote like that. You just want to sell more products. But this didn't come from me. This is from the International Code Council themselves, in what is a really helpful guideline document that I think, not enough people are aware of. It's the ICC G2 2010 Guidelines for Acoustics. It's a free document. You just Google that. You can find it. You can go find this quote. And there's guidelines for higher levels of acoustical performance in there, which we'll touch on in a second. We don't really have a poll thing. I set this up in the past for presentations where we've done polls, but I'm curious if anybody wants to just chime in the question section. What sources do you use to find acoustically tested assemblies? Maybe it's manufacturers, maybe it's the GA Fire and Sound Design Manual, or it's prescriptive things like the city of LA has like pre-approved assemblies for both acoustics and fire, those kinds of things. Just curious to see where people go for that information. So those higher levels of acoustical performance that are recommended in this ICC guidelines for acoustics are what you see here on the screen. So if it's a field test, the acceptable performance level is a 52 for either airborne or impact sound, and the preferred is a 57. And remember, the code minimum for a field is a 45. So these are considerably higher than that, right? And if you're looking at a lab test, they say the acceptable is a 55 and the preferred is a 60. And again, the code minimum is 50. So we kind of go in these like roughly like 5-point tiers. The interesting thing to me always about this is if they call this like grade B acceptable performance, that sort of implies that the code minimum is unacceptable, which seems strange for me for the Code Council themselves to state it that way. But I think that says something about the code minimum itself. So those are the acoustical sort of like a little bit of context on ratings and things. And the idea is that oftentimes we're not just shooting for that code minimum, we're striving for something higher. And what are the things that we need to consider when we're going for those higher code, higher performance values? And that can make all of the details of how we build and design these assemblies matter more, right? Similar sort of thing with fire ratings, right? So we have 1 hour fire ratings, very common for demising walls, quarter walls, things like that. But we also have 2 and 3 and 4 hour fire requirements. What do those actually mean? And when I was working as an acoustical consultant, before I really started digging into fire, I'd seen those like on architect's plans and things, but I never really knew what it meant or thought a whole lot about it. And coming to PAC, kind of the way that it's been described to me and discussed is, it's about not making sure that the thing is fireproof, right? Like I hate the term soundproof, and it's also like we're not talking about that it's fireproof. It's just gonna withstand fire for a certain amount of time to give people the opportunity and give them enough time to get out of the building, and also to give firefighters time to get in to help the people that are in the building that still need help. And so that's why for much taller buildings, we have higher fire rating requirements for egress passages, stairwells, and things like that, because it takes people longer to get out of those big buildings. So that's really what those mean. And so again, I'm curious, just, put it in the questions or whatever, what sources you go to for finding fire rated assemblies. Maybe it's the GA manual again, or maybe it's UL, maybe it's ICC ESR reports, different things like that. I'm just curious where people go for that kind of information. So another thing that, like, when I was working as an acoustician, I didn't really know about is where those ratings came from. I knew something about where the acoustic ratings come from, how those are tested. I went and did a lot of field tests myself, so I knew those fairly well. But fire tests, I didn't really know. And so Fire tests are done similarly to the way that we do lab acoustical tests, and that we have some sort of, sort of certified chamber, right, with a specific design, and we build an entire assembly, sort of to make up one plane of that one side of this box. And in a fire test, right, we're building either a wall or a floor ceiling assembly, and that makes up one side of a furnace. And then they make a fire in that furnace. They've got these burners, and they follow this time temperature curve that you see on the screen. And they just set fire to the thing, and they see what happens. And you're going for a certain amount of time, whatever kind of fire rating you're going for. And there are 4 pass-fail criteria, and I'll just kind of go through those briefly. So one is the thing has to stay together, right? Like if you're going for a 1-hour rating and the whole wall falls apart and collapses before you hit that 1-hour mark, clearly that's failed the fire test. The next one is the fire can't pass through it. So maybe this wall stays intact, the studs are still there, some of the gyps hanging on, but the fire is burned through both sides and it's reached the other side. It's no longer working as a fire protective barrier, and it's failed the fire test as well. The third one has to do with temperature, not actually like failure. So they will put thermocouples like thermometers, temperature sensors at different places on the assembly. And so they have some that are on the non-fire side of the assembly. And the temperature at those thermocouples on the non-fire side can't increase more than a certain amount. Again, I'm not a fire expert, so I don't know exactly what that certain amount is. And I don't know if this is exactly where this standard comes from or where this criteria comes from, but the way that it's been explained to me that kind of helps me wrap my head around it is if you've got a floor ceiling assembly, right, and the thing's still structurally intact, it's still there, you can still walk on it, it can still carry a load, and the fire hasn't burned through so that the fire is shooting up through the floor. But those things are still there. But if the floor surface is gotten so hot that it melts the boots off the firefighters when they come in to rescue people, it's still not a functional fire protective membrane, right? And it doesn't meet that requirement of egress, right? So that's the third one. And then the last one only applies to walls, and that's a hose stream test. So you have the wall that's in the furnace, you've set fire to it for however much time, it's burned and everything like that. And if it's passed the other 3 criteria, then you pull it out of the furnace and you take a fire hose and you spray it down. And that hose stream from the fire hose, it's gonna break through almost inevitably the fire exposed side, especially if you're talking, gypsum board partitions, but it can't break through the other side of the wall. So those are the pass-fail criteria. And I think it's helpful to just sort of like understand that context. And I think the big takeaway that is important for this and for acoustical tests is the way we test these is we build an entire assembly with all of the different components of it all put together like we would in the field, just in a very controlled laboratory environment. So not quite like we would in the field, but we build the whole thing and we test that. So it's not testing individual pieces, it's testing all of them in a group together. So we have how they perform together and how they interact with each other. And it's those interactions for both acoustics and fire that drive a lot of the design decisions that we make and a lot of the conflicts that we run into and we'll talk about in this presentation. So let's get into some of those details. And first, we're going to kind of just talk about some of the details of just really the fire ratings and the acoustical ratings, right? We sort of talk about them in these sort of broad terms, but we need to look at those details to better differentiate them and make safe decisions. Just like when we're out foraging for mushrooms, which is common here in the Pacific Northwest where I live, it's not good enough to just be like, oh, this is a mushroom. You need to really be able to identify that kind of mushroom, pay attention to the details, because otherwise it could make the difference between a delicious treat and a deadly treat. So for walls, first thing I want to get at in these details is STC ratings and IIC ratings. We tend to talk for acoustical performance in terms of single number ratings like an STC or an IIC. And that's what the code and a lot of the other sort of guideline documents like the FGI or GSA requirements, those sort of tend to talk in terms of single number ratings. But they're not all created equal. So here's an example of that. So we have 3 STC50 walls. Now, in terms of their construction, their makeup, right, they're pretty different. 2 are wood stud walls, one's a CMU block wall, but one of the wood studs is single stud, another one's double stud, it's got a clip and all this kind of other stuff in it. But they all wind up with the same STC rating. But the question is, if you were to stand on one side of each of these walls and have the same noise source on the other one, like a speaker playing some song, right? Is what you would hear going to be the same on the other side of each of these walls? And the answer is no, not at all. And the way that we can dig into this, we do this a lot as acousticians, is we look at this graph that you have here on the left. So I have another presentation, AIA accredited presentation that really dives deep into this. Check that out if you're curious more about this. But for now, on the horizontal or the x-axis, we have frequency, and it goes from low frequency, I think like bass guitar, kind of like subwoofer, rumble on the left side, to high frequencies, just like high-pitched screeching, right, on the right side. And then on the vertical axis or the y-axis, we have the transmission loss, and that's the noise reduction from one side of the wall to the other. So higher numbers of transmission loss are better, get more noise reduction. So again, all 3 of these walls are an STC50, right? But if you look at those curved lines, they're color coded, so that curved line gives you the transmission loss for a specific wall at each frequency. You can see that the green line for the CMU block wall is by far the highest at the really low frequencies, right? So at 63 hertz, it's 15 dB or more above the other 2 walls, right? So big difference. But then if you go and you look at the other end at the mid frequencies, say like 1000 hertz, it's the lowest performing, right? So it's gonna block the low frequencies better, but let through more of the high frequencies compared to the other walls. The blue wall, this big like double stud, double shear wall with a clip on it and all this kind of stuff, has lower performance down at the low frequencies. Not as bad as the single stud wall, but not as good as the CMU block wall. But at the mid and high frequencies, it performs way better than the other 2 walls. So if we're using an STC50 to just specify our acoustical performance, we're not really getting the whole picture, right? And if we have something like a home theater or a band rehearsal hall or something like that, where we're particularly concerned about low frequency noise, then maybe that single stud STC50, 2x4 wall with Brazilian channel, maybe that's not the best option. And maybe we need to look at something with more mass, like the CMU block wall that does well at low frequencies. But then we also have to consider mid and high frequencies, right? So there's a lot more details to pay attention to beyond just the STC rating. In a similar fashion, we'll do the same thing for IIC. So here's some floor ceiling assemblies, all very different constructions, right? We've got a wood open web truss, we've got steel C-section joists with springs for the ceiling, and we've got a concrete slab with a floating floor on top of it. But they all happen to have actually tested in a real lab at IIC 60. So here again, we have a similar graph. X-axis, the horizontal axis on the bottom is the same. Low frequencies on the left, high frequencies on the right. But here the vertical axis is different. So here the vertical axis gives us the impact sound pressure level. So that's when we do the IIC test, we have this little tapping machine that bangs on the floor up above. The impact sound pressure level is how loud is it down below at some particular frequency, or like a note on the piano, basically. So here, lower numbers are better because it means it's quieter. So you can see that there's still some variation, right? Like at low frequencies, here the green, the concrete slab, the heaviest assembly again, actually did the worst at low frequencies. Now, not huge differences, and it did the best at high frequencies. Whereas the red did the best at low frequencies, has the lowest numbers, but at mid frequencies, it's the highest. Right? So they perform differently in sort of different frequency ranges. So they're all still going to sound different if you're standing below them, even though they have the same IIC rating. So we would need to consider that again too for just sort of not just the quantity of the sound, but the quality of the sound in the space down below. And there's a lot of information here, and it's like, okay, well, this is like, okay, so I need to pay attention to these details, but what do I do with this? This is really complicated. And really the short and sweet answer is hire an acoustician, right? Acousticians are used to looking at these. They're trained in processing this information. And depending on the space and how critical it is, they may spend a lot of time going in and looking at this, actually doing sound transmission calculations. They might even do sort of modeling or auralizations to figure out what it's going to sound like on the other side, so that they make sure that they're really coming up with a wall or floor ceiling design that works for that specific use case. All right, so now let's kind of look at fire, but still in terms of acoustical performance. So something that like I've seen sometimes show up in architectural drawings or whatever is a wall that needs to be acoustically rated. Like say it's a demising wall between two apartments, right? It will be specified in the architectural drawings and the assembly drawings, but just based off of a UL design. And not necessarily a ton of construction details directed at the acoustical performance. And these might be design build projects or something like that, where the architect has a smaller budget, or there's sort of delegated design for steel stud walls and things like that. But so let's just run down that. Let's say we just specified a wall based on a UL design. So let's take UL U465. Well, the three walls you have shown here all sort of meet the minimum requirements or exceed those minimum requirements of UL U465. So I think U465 is a non-load bearing steel stud 1 hour rated wall. So you can use something as thin as an 18 mil, like a true 25 gauge stud. These days you see a lot more sort of like EQ studs where they use thinner steel but rely on the shaping to make it stronger. So up at the top, we have a 20 gauge EQ or a 19 mil steel stud. It's an STC 48, just a single layer of chip on each side. Meets the requirements of UL U465. Not the best acoustical performance, but might work for like an office wall or something like that. The one below that uses a 12 gauge 97 mil steel stud. And that's a very burly, beefy stud, but it's the kind of thing that you might use in a load-bearing steel building where you've got many, many floors above this, and so you need these big, heavy studs so that you can keep your wall footprint slim, but still carry all that weight. And you can see you lose 10 STC points just by changing the thickness of the steel, basically, and reducing the stud spacing. The last one on the bottom left uses 20 gauge steel studs. I'm not actually sure the mil thickness on these. That's an important thing to pay attention to. But this uses a resilient sound isolation clip for isolation to isolate the drywall from the studs, and it's got more layers of gypsum board. It exceeds the requirements of U465 for fire, but it still fits within it. And acoustically, it provides much better performance than the other walls. So we need to pay attention to not just the details of the fire rated design to make sure that we're following our UL design or what we're pulling out of the Gypsum Association Fire and Design Manual, but we also need to pay attention to the elements that affect acoustics. And we'll go in and we'll talk more about some of those. But layers of gypsum board, isolation, stud mill thickness, spacing, all of those things do matter. All right, and not to belabor the points too much, but here's an example for floor ceiling assemblies. So we'll take L546, a wood open web truss. And again, these are all, these are all assemblies that meet the design of L546. They hit those minimums or they go beyond it. But acoustically, they're very different. We can see that the IIC rating, so the impact insulation class, varies from a low of 40, so that's 10 points below the multifamily code minimum, to IIC 70, which is even 10 points above the preferred grade of 60 within that ICC document, right? So again, we need to pay attention to the details for fire, obviously, for fire life, for life safety, but we also need to figure out those details and pay attention to them for acoustical performance as well, because a fire design does not necessarily specify good acoustical performance. So how do we make sure that we can pay attention to those two sets of details for fire and acoustics and other things like cost, constructability, structural integrity, all of these kinds of things? How do we sort of bring all of those things together and come up with a design that satisfies all of those? That can be really tricky, and that's sort of where the rubber meets the road, right? So we come up with these tensions in the design team, and we'll talk through some of those. So I have 4 things here. I've got this little animated graphic where we'll kind of talk through these. So the 4 things I want to talk about are resilient element spacing. So that could be resilient channel or like sound isolation clips and hat channel. And then layers of gypsum board. I think that's self-explanatory. Stud spacing, also self-explanatory, and screw spacing. And here when I'm talking about screw spacing, I am specifically referring to the screw spacing for attaching the gypsum board to whatever the structure is that holds it. It could be hat channel and clips. It could be, you know, directly to the studs or the bottom of a joist or, you know, whatever that may be. So we have 4 characters that we're going to look at here. So going from left to right, on the left, we have the developer, right? She's got the money in the suit, right? That's the developer, represents the money sort of perspective in this. Then next with the calculator, we have the structural engineer. And next one, firefighter, pretty obvious, it's fire protection designer. And then the last one is the acoustician. So we'll start through each of these and we'll kind of see where each one of these wants to go on this kind of like continuum that we've got. So if we're talking about resilient element spacing, the developer is going to want it wider spacing. It means less material, less labor, cheaper, right? Saving costs. The structural engineer may not care necessarily because oftentimes those resilient element spacing, those resilient elements aren't part of the structural design. But in some instances, if they are, or even if they're just looking at like the support of the gypsum board or something like that, I have had structural engineers question spacing resilient channel or hat channel at 24 inches on center. Totally fine, done all the time. It's allowed in a lot of the UL designs. But structural engineers, they just want more structure, right? They want to make sure they've got those safety margins and things like that. So they're going to go for narrower spacing, more structural support. Fire protection engineer also wants narrower spacing. And the reason for this is that in those fire tests, right, when you've got this assembly, like let's say you've got a floor ceiling assembly and it's in that furnace and you've got these flames coming up and they're heating up that gypsum board. That gypsum board is the fire protective membrane. It's what is keeping the fire from getting to, let's say, your wood joists and burning them so that the whole thing collapses, right? So we want to keep that fire protective membrane intact as long as possible. And what happens in the fire is gypsum board has water in it. And as the fire heats up that gypsum board, that water turns to steam and it comes out of the gypsum board, right? And we call that process calcining. And so the gypsum board sort of kind of goes back to like raw gypsum, or I don't know all the, you know, again, I'm not a fire expert, I'm not a chemist, but what happens is the gypsum board gets crumblier, right? And it'll start to kind of crumble and fall apart. The more support you have for that gypsum board, the longer it can hold together as it kind of starts to crumble and lose its internal cohesion. So we want more support for the gypsum board that's going to make it hold together longer in the fire. In acoustics, we want wider spacing. So we can look at this resilient element spacing. We're looking at the sound transmission from one side to the other, right? And the fewer connections that we have, the less space there is, the less surface area there is to transmit that energy from one side or the other. You can think about it a lot like thermal bridging, right? Like if you're designing a building envelope, it's great if you have this, you know, R21 insulation between your studs, but your studs are a thermal bridge that will conduct heat, and so it will reduce the overall thermal, you know, the insulation of that wall. And the more you can reduce those connections for those thermal bridges, the less heat transfer you get through. Same thing for acoustics. The fewer connections you have from one side of the wall to the other, the less opportunity there is for that acoustic energy to get transmitted from one side to the other. So we want wider spacing, fewer connections. All right, layers of gypsum board. Developer wants to just pay for less gypsum board, right? Save money. And also labor for installing gypsum board is not cheap, and it's certainly not getting any cheaper. So fewer materials, less labor, save money. Structural engineer. Now this one may or may not make as much sense, but structural engineer often will actually want fewer layers of gypsum board. And there was a project that we were working on not too long ago. I think it was out on the West Coast where seismic, right, is a big issue. And so in this case, the structural engineer was looking at the amount of the mass of the gypsum board, especially higher up in this building, because that was going to increase this mass, this inertial mass that was moving back and forth in a seismic event. And the more weight there was up there, the more stiffness they had to put lower down in that structure to resist that weight moving back and forth. So if you take weight out, then you have these knock-on effects of needing less structural integrity, you know, down below, and that saves you money, right? And those can be pretty significant if you've got a big tall tower or like a lot of extra weight from gypsum board or whatever it may be. Fire protection engineer wants more gypsum board. It's the fire protective membrane, so we want more of it, right? And you know, in walls, like one of the common ways you'll increase the fire rating is just add more gypsum board to it, right? And in acoustics, we want more gypsum board too. Mass sort of resists that movement. Sound moves from one side of a wall to the other. Sound is air pressure waves, and so it's those pressure waves making the wall move, and then that makes the air on the other side move. The heavier that wall is, the more energy it takes to move it. So more mass, more sound resistance. All right, so stud spacing. Again, developer wants wider studs, less labor. And in talking to a lot of estimators for drywall and steel framing companies, they'll say that they'll always try and push to using 24-inch on center stud spacing, maybe not always, often when it makes sense, they'll push to wider stud spacing, but a thicker stud, because the increase in material cost for the thicker stud is more than offset by the decrease in labor, because labor just tends to be much more expensive these days. Structural engineer wants narrower spacing, right? Stronger, stiffer. I think that one's fairly straightforward. Fire protection engineer also wants narrower spacing. Again, more things to attach to gypsum board, and it's more likely to stay together during the fire as it starts to sort of crumble and want to fall apart. Acoustically, we tend to want wider studs. Now there's, I just did a whole webinar on steel studs and parameters of steel studs and how they affect acoustical performance. And there's some interesting conversations in there about steel studs and spacing. But generally kind of the rule of thumb and general thought is that wider stud spacing tends to do better acoustically. And you see that if you look at tests for, you know, studs at 24 inches on center versus 16 inches on center. Acoustically, we just want fewer connection points is a lot of what it comes down to. All right, last but not least, screw spacing. Again, this is for attaching the gypsum board to the structure. So again, fewer screws, less labor, less money. Structural engineer probably doesn't care too much about the screw spacing for attaching the gypsum board, especially to things like resilient channel and hat channel, because it's just not part of the structural sort of calculations. However, if you've got gypsum board attached directly to like a steel stud, if you want to use the composite wall height tables, those specify maximum spacing for the screws to attach the gypsum board to the studs. So in some instances, it does matter to the structural engineers. And in those instances, they're going to want tighter screw spacing, narrower screw spacing, because it's more attachments, it's stronger, right? Fire protection engineer wants narrower screw spacing. Again, it's more things holding that gypsum board together as it starts to calcine and kind of start to fall apart in the fire. There's more screws means it's going to hold together longer. And acoustically, we want wider screw spacing. Again, fewer connection points means fewer points to transmit acoustic energy. So there's a lot of things in here. And kind of one of the big takeaways from this is that kind of changes depending on what element of the design we're looking at. We have different people sort of partnering up on the same sides, right? And another thing that I thought was interesting from this, just from my own personal experience, is working as an acoustician for 10 years. I often felt like I was at odds with the developer because a lot of what I was suggesting was increasing costs. But as I went through this exercise, I was happy to find that in 3 out of the 4 scenarios that I put here, the acoustician was actually on the same side as the developer. So we're not always the enemy. We're not always trying to drive up costs on the project. And there can be some instances where the things we do could actually reduce costs. So a little bright side for acoustics there. All right, so rules of thumb and how they could be dangerous. Love my cheesy little animation there. All right, so rule of thumb I'm going to talk about, just to use as an example, is insulation and the amount of insulation that you have. And I would say within the acoustics community, at least, sort of there's this general rule of thumb that is, if you've got a cavity, like a floor ceiling cavity or a wall cavity, if you've got no insulation and you add some insulation, that's really good. It'll improve your acoustical performance a lot. But then adding more insulation oftentimes isn't worth it. Necessarily doesn't give you like big gains. But really it depends, and we'll show you that. So we got a 2x10 wood joist assembly, OSB subfloor, resilient channel, and a single layer of gyp. Very, very basic assembly. So when we start out with no insulation in the cavity, we've got an STC 43 and an IIC 37. So nowhere near code minimums, not a great assembly. Let's add some insulation. So if we add 90 millimeters, about 3.5 inches of insulation, our STC goes to 51 and our IIC goes to 45. So that's an 8-point improvement for adding 3.5 inches of insulation. And if you think back to those ICC guidelines, they kind of went in 5 points for the different tiers. So 8 points almost moves us up 2 full tiers. So that's a big improvement, right? But then let's say what happens if we just fill the rest of the cavity. These are 2x10 joists, so 235 millimeter, you know, for a true like actually 9.5 dimension. And they actually overfilled the cavity, which is fine. It's not bad acoustically. And they got like another 1 or 2 points, went to 53 and IIC 46. And if you actually look on here, you can see that even down to like the 152 millimeters, like once we hit that 3.5 inches, the insulation didn't really change the ratings much at all. So you're like, adding more insulation, totally not worth it. Don't do it, waste of money. Well, but let's look at a deeper assembly, right? So these are eye joists, and I think these are 457 millimeters. So they're like an 18-inch eye joist. So here we don't have an empty cavity, but if we start with 3.5 inches, we're at STC 52, IIC 46. And here we fill the whole cavity, we get 5 points in the STC. So that would move us up a tier, right? And 3 points in the IIC. Not as much, not quite moving up a tier, but 3 points is a noticeable change in the IIC rating. Might be worth it. So the idea is, like, if you just looked at that one assembly, this one context, you might conclude this rule of thumb that, you know, once you've got some insulation in there, adding more isn't worth it. But in this another assembly, that's not necessarily the case. It might be worth it, especially if you're trying to hit some particular target that's code prescribed or whatever it may be. You know, adding more insulation could be a way to get you there. And maybe it's a way that makes the most sense. But we got to pay attention to fire for that too, and we'll come to that in a little bit. All right, so here's where we're going to talk about the fire part of that for insulation. So we're going to talk about 2 different design elements, insulation thickness and resilient channel spacing, and how the interplay between them in terms of acoustics and fire. So here, as an example, we have a UL design, L587, I believe it's a 1-hour wood open web truss design. And within the UL designs, if you've spent some time reading through them, digging into them, you'll know this, that there's a lot of variation in like resilient channel or like hat channel spacing and with insulation thickness. There's a lot of different permutations of these. So what we'll start with here is, let's see if I can add a little marker here. So first off, we've got this assembly in the top left. So cavity, no insulation in the cavity. And when you have no insulation in the cavity, this UL design says you can have your resilient channel spaced up to 24 inches on center, okay? But we just saw from that other example that adding insulation is really good for acoustics. So let's go to that sort of first tier of 3.5 inches of insulation, because we saw that we could get like 8-point improvement, right? So we want to get that benefit of it acoustically. But the UL design says if you have up to 3.5 inches of insulation tied up to the bottom of the subfloor, and the positioning is important for fire, if you got 3.5 inches tied up to the subfloor, you have to reduce the resilient channel spacing to a maximum of 16 inches on center. If, for whatever reason, you wanted to put that insulation down low, drape it over the resilient channel and the back of the gypsum board, the UL design, this one says you've got to reduce the resilient channel spacing further to a maximum of 12 inches on center. And if you do anything more than 3.5 inches of insulation anywhere in the cavity, whether it's up top or down low or in the middle or whatever it is, you also have to reduce the resilient channel spacing down to 12 inches on center. So increasing the insulation is good for acoustics, but what happens about decreasing the resilient channel spacing? So now let's look at that. And for whatever reason, it doesn't work for me to click when I have the little highlighter thing. So here's what it looks like in the UL design. So I put this up here. I know you're not supposed to put a bunch of text in presentations. I try to avoid that, but I put this up here kind of to be overwhelming, right? Like reading these UL designs can be confusing. I've spent a lot of time digging into these, and it took me a while to kind of understand all of the ins and outs of these, and they're all a little different. A lot of times the guidelines on resilient channel spacing or hat channel spacing, if it's with clips, that resides under the section for bats and blankets for the insulation. Sometimes there's additional guidelines for this under the resilient channel or the clips and hat channel. You'll find some of it there. There might even sometimes be some guidelines for this under the gypsum board sections. So you kind of got to look all around for it and find all of the different sections that apply to the materials you're looking to make sure you've got it all covered. And sometimes they might even be slightly at odds with each other. So good luck, and reach out to somebody else. You can feel free to reach out to PAC if it's working with our products or other things to try and navigate those. So acoustically, what happens when we increase the insulation thickness but decrease our resilient channel spacing? So again, using this baseline 2x10 wood joist assembly. So on the right, we have changes in insulation thickness, and on the left, we have changes in resilient channel spacing. So on the right, we're going to go from empty cavity, and on the left, we've got 24-inch on center resilient channel spacing with an empty cavity. So now we're going to add 3.5 inches of insulation, right? But that means our resilient channel spacing has to go down to 16. So we saw before that adding that insulation gave us 8 points. And here I'm really focusing on the IIC ratings because that tends to be more challenging and drive our acoustical design for floor ceiling assemblies. So we got 8 points for adding the insulation. But what happened when we reduced the resilient channel spacing to follow along with the UL design? Well, we lost 4 points for our IIC rating. So we thought like, oh yeah, add some insulation, we'll gain 8 points. But realistically, when we combine it with the fire design, we're only going to get 4 because we lose 4 points for decreasing the resilient channel spacing, which is required by the UL design. So not as beneficial as we would hope, but 4 points is still enough to basically move us up to another acoustical tier of performance. So still probably worthwhile. So then what happens if we add even more insulation? Well, we go to full cavity, almost actually overfilled, and we gain 1 more point for IIC. Not noticeable, right? But we also have to reduce the resilient channel spacing. And here in this particular instance, it didn't make a difference. So we still gain a point, but not that helpful. I don't have data for that other 18-inch TJI assembly, but it is possible that there we gained more performance for filling the cavity, but there we might also see some actual decrease in performance for reducing the resilient channel spacing, or maybe not. So all of this is sort of context dependent, right? It's not about just the individual parts and what they do, but how they all interact with each other. And that's why this gets really complicated and managing it for acoustics and fire. So the thing is, you got to pay attention to the details and the context within which you're operating. So generally speaking, I know I just said rules of thumb are dangerous, so just, you can use them, but with caution. If you increase the amount of insulation, you increase the isolation. But when you increase the amount of insulation, you have to decrease the RC spacing, which typically decreases the isolation. So these two things are at odds with each other. And you got to find sort of the balancing point. to optimize the design. So that's complicated. So how do you work through all of that? Well, one of the ways on the acoustic side is you reach out to an expert in acoustics. How do you find them? Two good resources are INTS USA, the Institute of Noise Control Engineers. There's a directory there, and then we also have NCAC, the National Council of Acoustical Consultants. So check those out. All right, next one, stud gauge and spacing. And I've done a long webinar on this, but we'll just do this briefly. And I know we're kind of getting close on time, so I'll try and go through these a little bit faster. So UL wall design, U465. It specifies minimums. Typically, the UL designs are given in terms of minimums and maximums. So here there's a minimum depth of the studs, a minimum stud gauge or thickness, and then a max for the spacing, right? So here we have two walls that both comply with that, but there's a big difference again in their acoustical performance because the stiffer, much stiffer 12 gauge steel studs spaced closer together transmit a lot more acoustic energy, sound energy from one side to the other. So again, you got to pay attention to those details. But obviously, structurally and for fire, maybe the stiffer, stronger studs are going to be better. All right. So minimums, and here's the difference in those studs, right? All right. So another example where sort of managing acoustics and fire in conjunction with each other can be tricky is 2-hour floor ceiling assemblies. So a lot of the 1-hour assemblies, our acoustic isolation goes between the bottom of the joist or truss or whatever it is and the gypsum board. So we have structure, acoustic isolation, gypsum board, right? 2-hour assemblies tend to be different. Many of the 2-hour rated like wood assemblies will have a layer or more of gypsum board attached directly to the bottom of the joist. And then resilient channel or clips and hat channel, like an air cavity, and then one or more layers of gypsum board. And you can see that here, especially in this bottom picture, right? You see this RC sandwich is what we'll often call it, right? Well, that is not good acoustically. So I'll show you from some test data from the National Research Council in Canada. So at the top, we have very basic floor ceiling assembly, one we've been looking at already. And this tested at an STC 52 and IIC 46, resilient channel, and some insulation in the cavity. And if you've been paying attention, you'll know that this assembly probably actually wouldn't meet a UL design, wouldn't be a fire rated design because of the RC spacing and insulation thickness. The one below has sort of that typical 2-hour fire rated ceiling design, right? That RC sandwich. And you can see the STC rating dropped by 14 points. That's a huge reduction. And then the ISC actually dropped by 15 points, also a huge decrease in the impact isolation performance. So even though we added more gypsum board, we added mass, which should be good for acoustics, but the way we did it is bad for acoustics, this little bitty air cavity. And for some more context for this, if you just eliminated the resilient channel altogether and had just attached the gyp to the bottom of the joists, like this was just single family residential construction, it's an STC 33 and ISC 28. So not much worse than the sort of like 2-hour fire rated kind of ceiling. So if you've got this, what do you do? So like we've worked with an architect in New York who's done a number of different projects where they've got sort of ground floor restaurant kind of a space. It's a restaurant, coffee shop, bar, whatever. Some of them might have DJs, live bands. And then they've got apartments or condos directly up above. These are older buildings, wood framed construction, but you've got these two separate sort of use types. So it typically has to be a 2-hour rated assembly. How do you build it for fire, but also get really high levels of sound isolation because of the two very disparate uses? So it can be really tricky, and finding a 2-hour fire rated design with acoustic isolators in it that will work for this situation is really tricky. There are some, but often what you wind up having to do is treat the acoustics and the fire separately. And that's what you'll see in these examples. So here we have sort of a basic assembly design, and then we've built it for fire, kind of ignored acoustics, and then we've added spring isolators down below as an acoustical upgrade. And that's what we've done on a number of those projects in New York. It works really well, but spring isolators can be expensive. They also take up a fair bit of space. You might not always have the space to drop your ceiling that much. So another option is to just use sound isolation clips and attach them directly. It takes up a lot less space, but it also doesn't work as well acoustically because you still have this fairly small air cavity. This one's bigger and it's got some insulation. We can fit some insulation in it, but it's still not as great, but it might get you there depending on what your target is, right? And what your noise source is and that thing. Sometimes you might not be able to do anything on the bottom side. Maybe you're working with a tenant who's renovating that upstairs space and they don't have any control of what's going on downstairs. There you might use a floating floor. And again, it's not part of the fire rated design, but it's the sort of acoustical add-on. And like I did this as an acoustical consultant on a project. I was helping design sound isolation and everything for a recording studio that they wanted to build directly above a brew pub. Great if you're the musician recording in there and you want to go down and grab a beer like during your break, that's awesome. But when in the brewery they're like dropping kegs and moving kegs around and you're like just recorded your perfect track, but it was destroyed by like this loud thump and bang from down below, not so awesome. So we had to do all the isolation on the top side and we did a floating floor there. All right, last thing, and then I think I'll wrap this up, wall ceiling intersections. So these can be really tricky again for managing acoustics and fire, because for fire, we want things sort of rigidly connected so that the fire can't get through. And for acoustics, we want things not rigidly connected so that the sound can't get through. So those are sort of at odds with each other. So in wood frame construction, it can be fairly easy. We can use like the design on the right where it's a fire rated partition and demising wall, unit demising wall between two different units. So we need fire and acoustics. At this intersection, in the middle here, we can stop the gypsum board so that the gypsum board's not connected anywhere. It's not continuous. It's not going to help transmit sound through. But the studs here are all sort of blocked together in this corner. And the stud, the wood stud, can interrupt the gypsum board typically because it's approved fire blocking, right? Because it's going to take a while for the fire to burn through that. So this works for wood stud construction. But in steel construction, it's a little trickier. So if we have a fire rated wall, unit demising wall like this, sorry, let me grab my spotlight, fire rated wall like this and acoustically rated wall, if these have the same fire rating, then typically it's my understanding that you can bisect this like corridor wall with this unit demising wall, right? Because it still provides the same resistance to fire, kind of whatever way you go. And then we can just make sure that all the gypsum board, there's gaps and they're caulked for fire and acoustics, right? And pay attention to all these details and sort of how the sound and fire and smoke can flow through here from side to side. So this one can typically work. You can't just use the stud to break the gypsum board because a steel stud doesn't work as fire blocking generally. On a, if it's within a unit, often we don't care about sound transmission from one side to the other. So this is fine. We keep this wall continuous. But there is this path, this continuous gypsum board that can transmit sound. So what if you have a situation like from, you know, one retail unit to another retail unit, right? In some like strip mall kind of space. And this is like another like back of house corridor where you need a fire rating, something like that, right? And this actually needs to be acoustically rated. How do you, or like an office and you want to get that separation, right? Well, if you do that and you have this wall break this so that this gypsum board is no longer continuous and a flanking path, but then this breaks the fire rated wall, so it also has to be fire rated, which maybe is okay if that's already part of the plan, but if it's not, that can significantly increase the cost of this wall. You got to add putty pads, you got to use different types of gypsum board, you got to use more screws to attach the gypsum board. There's all of these other things that you have to pay attention to. You got to get it inspected more. So that could be a big thing. So you got to pay attention to these junctions and how you manage them. And they're really going to be context and sort of job specific. So I can't give you like prescriptive, like always do it this way, because it's kind of always going to be different, I think. So Wall ceiling intersections are similar. Again, with wood, you can typically block this intersection. And so they can work for within units, sort of, or between units. You can get that separation. But again, in steel frame construction, you can't block that. So you've got this continuous path. And what happens is you can get the sound transmission from one side to the other. Same thing over here, right? So how do you do that? One possibility, and you would have to run this by your AHJ or whatever, but to break this gypsum board, sort of like a fire rated control joint. So you would just leave a little gap, but caulk it so that you don't get this continuous path. But those are some of the things you kind of got to pay attention to in these situations. So that's kind of the tension in the design team. So when you get into that, the last question, and I think I'll wrap up here after this, is who on your project teams is typically responsible for coordinating fire and acoustic details? And usually I find it lands on the architect, and the architect is sort of relied upon to be an expert in both of these really complicated things that maybe you haven't spent as much time learning about. So hopefully this has helped with that. So just real fast, and then we'll have a few minutes for questions. I want to thank Maxon Corporation first. I originally put this presentation together with, or a version of this presentation with Evelyn Way, who's Maxon's acoustician. So I want to say thanks to them for helping put all this together, give them credit. Pathco Gypsum, we work with them a lot. We do a lot of acoustical testing and things with them. Some of the test data in here that I relied on is from them. National Research Council of Canada, they also do a bunch of acoustical testing and fire testing. A lot of the other information I relied on in here is National Research Council of Canada. Good folks, got a lot of good acoustics data and research. And then last, the Institute of Noise Control Engineering. I originally gave this webinar with Evelyn from Maxon as a presentation to INTS as one of their webinars. So thanks to them for sort of being the impetus for this presentation. And with that, we got a few minutes, and I think we can stay a few minutes past the hour. We got some time for questions.
Thank you, Mike. A couple of, let's see, your responses to your questions during the presentations, where do people find their fire rated assemblies? They were all of the ones that you mentioned, GA Manual, UL, and ICC reports. That was the only, yeah, the only response to that one mid-presentation question there.
Okay.
Mm-hmm.
Well,
no other questions.
Yeah. Not missing something. So no other questions. I did see there's one. Is there a handout to download? Yeah, and I think you already said that we have recordings of this, prior versions of this that I've given that are on our website on our webinars page, and then we will get a recording of this and we'll probably put that up there as well. And also, just in case the question comes up, we do not have some sort of like thing laid out where you can just go watch the video and get credit. We're only registered with AIA for this to be like a live presentation that you got to sit through. So, but we'll give more of them. I think we've got another one scheduled for next month as well. So, and then, yeah, no, if there's no other questions, nothing else, Steve?
Nope, no other questions during the presentation or posed in the chat there. So.
All right. Well, I guess I just covered it all. No, I'm sure there's lots of questions.
You solved it all, Mike.
No. I probably just raised more questions than anybody wants to. Here's our contact info. So if you do have questions or some particular project or thing you want to dig into, here's our contact information. My email, mrayleigh@PAC International. Especially if it's like acoustics related questions, feel free to reach out to me directly. Trying to find acoustic test data and ratings and things especially can be difficult. I know I was always trying to hunt down test data as an acoustician. So when I came to PAC, one of the first things I did was put together a way for people to go access test data without having to email somebody and wait for them to respond. So we have this database. The registration link is there. If you go register, then you get access to what you see here, where you can go filter by STC, IIC rating, UL design, structure type, all of these different things, and see if we've got a test, an acoustical test for an assembly kind of similar to what you're looking for. And so you can go around, play around in that, and if you can't find something, then reach out to us. The other thing we have is a fire design selector. So you can go look for specific UL designs and see if our products are in them. Or you're like, I want to use like a resilient sound isolation clip in a 2-hour wall. Can I do that? What walls is a sound isolation clip in? Or you can come in here, you can filter through and see which ones it's in, if it's in any. So they can be really helpful tools. We've also got some details, CAD drawings showing you how those walls and things go together.